Tak vás veľmi pekne vítam na dnešnom druhom bode programu, vedeckého programu na festivale Pohoda Sporka Science and Magic Stage. A len vám chcem povedať, že ak ste náhodou zmeškali niektorý zo včerajších bodov programu, ktorý by vás zaujímal, tak všetko sa filmovalo a čoskoro sa videá objavia na YouTubeovom kanále Fakulty matematiky, fyziky a informatiky, takže sa tam môžete zájsť pozrieť, ak by ste si niečo chceli pozrieť znovu. And now we switch to English since we have our only English-speaking guest today, and we are very happy to have Professor Roger Jones from Lancaster University, who is experimental particle physicist in CERN, and he's going to tell us what's the matter with antimatter.
Thank you. So, dobrý den. That's the only Slovak I'm afraid you'll get from me today. So yeah, I'd like to tell you a little bit about antimatter. If I'm speaking too quickly, somebody wave, because I do talk quite quickly, and I realize I'm an English speaker. Most people first encounter the idea of antimatter in science fiction. So, probably most famously, the Starship Enterprise in Star Trek is supposed to be powered by antimatter. They have these dilithium crystals which somehow magically capture antimatter, and then they use that antimatter to power the ship, and occasionally it manages to send them through time, so they do time travel from now every so often. My favorite science fiction program is probably less popular in Slovakia. I'm a big fan of Doctor Who. But good! I like to hear that, because you know, Doctor Who's been going on for 55 years now, and there's been antimatter all the way through it, with the modern guys and with the old guys. All of the different doctors have used antimatter. Great stuff. I could talk for about 3 hours on Doctor Who if you want. It also appears in other less good things. Sorry, am I allowed to say that? So antimatter featured quite a lot in the film Angels and Demons, if you saw that. I did. It's 2.5 hours of my life that will never come back. But it did feature the experiment quite a few of us here today work on, called ATLAS, the ATLAS experiment, the Large Hadron Collider. In fact, one of our technical guys from the Big Bang Collective who's with us, Chris's shoulder, appears in that film in one of the shots. He's very proud of that. But in that, a bad pope manages to get antimatter stolen from CERN and makes a bomb which is going to destroy the Vatican. Well, we'll come back to that in a bit. But the point is that antimatter is not a science fiction thing, it's very real. And actually, it's used in everyday life. It's practically useful. I hope the people in the audience have not needed it, but we'll come to one very important application that appears in many, many hospitals. And it's produced in large quantities for particle physics experiments in particle physics experiments. But it does pose one really big question about how we are able to be here today to have this talk, because there is a fundamental question still to be answered about the behavior of matter and antimatter, which we're still working on. That's one of the things I'm working on at CERN. So antimatter was first proposed by, I'm calling him a British physicist. He was born in Britain, but of Swiss parents, so the Swiss claim him as well, a guy called Paul Dirac. And he proposed antimatter in 1931. And he'd been doing something really interesting for a physicist. He was trying to write down an equation that at the same time obeyed the rules of quantum mechanics and of relativity. So first I'm going to tell you just a little bit about those two really revolutionary ideas of 20th century physics, and then we'll see how they fit together. So relativity was something that was a theory that was created largely by Albert Einstein, but others made important contributions. And it was trying to address a really weird problem that had been observed experimentally. If you obey the laws of physics that you were probably taught at school, I'm going to go back to my original helper, please. If I throw this ball at my willing victim, it travels at a certain speed. He doesn't like having that ball thrown at him. He's going to run at me and throw it back. Ah! That'll do. So from all the things you were taught at school, the ball was traveling faster when he ran at me and threw it than when I just threw it, even if we just gave it the same push. Because he's running, the two velocities add together, and the ball is traveling faster in that case than the first case. But what was discovered experimentally, and it's been repeated forever, over and over again, if you look at light, it doesn't matter whether you are moving towards the source of the light or the light source is moving towards you. You always measure the same speed of light. And that just cannot be explained by the laws of physics as written down by Galileo and by Newton. And it required a new theory which Einstein put together called relativity. And when you do that, you get all of these really strange effects that you'll have heard about from relativity. I can't talk about them all today, but you find that the apparent passage of time depends on how quickly you're moving. You find that light actually can be bent by gravity. That's a general relativity effect. And that you find that energy and matter are in some sense different aspects of the same thing, and you can convert energy into matter and matter into energy. That's what we do in our particle physics experiments all the time. We take a lot of energy and try and make new particles. We convert energy into matter. And that's governed by this equation. If there was one physics equation, we asked everybody, do you know a physics equation? They would probably come up with E equals mc squared. That tells you how you can relate an amount of energy, E, to an amount of matter, mass, m, and it's related by the speed of light. Okay, so that was a really revolutionary theory, which we could talk about for ages. But there was another really revolutionary theory that came through at the same time, and that's called quantum mechanics. So up until the beginning of the 20th century, people thought if you had energy, you can have any amount of it. It can go take any value you like. But then there were some very weird aspects, particularly of light hitting metals. We saw electrons being kicked out of the metals, and they had really weird behaviors. And it was found by Planck and others that the only way you could explain that is that the energy can't take any value, it can only take various discrete values. Well, that doesn't sound too troubling. But you take that theory further, and many people did, including people like Paul Dirac and many others, and what you find is that it's telling you, in effect, that A, things are quantized into different values, but it also then tells you that particles actually don't just behave like particles. In some circumstances, they behave like waves, and that waves don't always behave like waves. Sometimes they look like particles. And you have these really strange things, the uncertainty principles, which is just a reflection of the fact that if you really describe things in quantum mechanics, everything is really described by a wave-like object. It tells you, if I know, for instance, how fast something is going, precisely, I cannot know where that object is. And the more precisely I know where it is, the less precisely I know how fast it's going. And then there's another important relationship, which is if I know precisely when an event happened, I know less and less precisely how much energy there was in that event. So these are the Heisenberg uncertainty relationships. You've probably heard about those. That's really very weird. The relativity effects tend to happen at large scales and high temperatures. The quantum mechanical effects, you tend to observe them more at low, small scales, the tiny scale, like particle physics experiments, and at very low temperatures. But for a physicist, the theory that describes the world has to describe both of these behaviors. They have to fit together. So Dirac was working on trying to put quantum mechanics and relativity together in one theory and one set of equations. He wasn't the first person to do that, and many people had tried, but they said, there's something wrong with what we're doing. Because when they did that, they found that it was predicting states and particles that had a negative energy. And everybody said, but that doesn't make any sense. There's no such thing as negative energy. So they thought they'd got it wrong. In many ways, the genius of Paul Dirac was to realize that wasn't wrong. That was telling you about something new about the way the world works. By the way, those of you who've got a bit of a science background, even at school, you may have heard about particles having spin. Doing the same combination, he also managed to explain where that thing called spin that affects chemistry and things like that, where that comes from. So his picture that Dirac came up with about what happens when you put these two theories together was he said, look, what I think it looks like is that there are negative energy states, but we don't normally see them because all of those energy states are filled and you can't push any more particles into them, so you don't see them. And we're just dealing with all of these states way up here where they're empty, and you can move the particles between them. But what he then realized was, actually, if I've got a negative energy state, and I push some energy into one of the particles in that state, like make it absorb a particle of light, a photon, it will jump up from down here to up here. And what would that look like? Well, it would look like you suddenly see this particle, like the sorts of particles we've seen all the time. But what you would also see is that there is a hole left in that big sea of negative energy states. And he said that hole would have the opposite properties of the particle you took out of the hole. If you want to see how that might, just give me a little illustration of that. You may have seen this optical illusion. It's usually done with Einstein's head. You take a shape, and you take almost like a death mask. You push, and you get the shape of someone's face. If you light it correctly, and you turn it round, you can look at it where it's sticking out, and that looks like Einstein's face. But as you turn it round, you can also see something that looks like Einstein's face underneath. Let me illustrate that here. This is exactly one of these things. So that actually is a hole in the plaster. Actually, no, I think that's the bit sticking out. I can't tell the difference. Yeah, and the bit coming around the back is the bit where it sticks out. So both the particle and the antiparticle look very similar, but one is the hole and one is the positive bit. The realization was that this was not only a weird theory. I mean, people like Bohr, who was a really smart man and was one of the architects of quantum theory, said, this is nonsense. But actually, a poor old experimentalist like me, an American called Carl Anderson, had been looking at cosmic rays, like the ones that you could see in the cloud chambers that we were making in the workshop just before, and they'd seen this. They had seen a particle of light, which you don't see, going through, and then suddenly, particle going there and a particle going there. There's a magnetic field here. One bends one way because it's got a negative charge. It's an electron. The other one's bending the other way in exactly the same way, but in the opposite sense. That's like a positively charged electron. It's an anti-electron. It had already been observed in 1930 before anybody realized what was going on. Nobody had any real explanation for that. So antimatter is very real. Now, there is another property which you probably do know about from antimatter, at least from the science fiction, and that is that's basically turning some energy into a particle and an antiparticle. But you can reverse that. You can take antimatter and matter and put it together, and it will generate lots and lots of energy. It will generate energy obeying Einstein's equation, E equals mc squared. And actually, that tells you get quite a lot of energy for a tiny amount of matter. Now, there is a modification on this. That description of antimatter that I told you about is the original one from Dirac, Another really bright guy that you may have heard of, Richard Feynman, along with another great theorist called Stuckelberg, they had a different interpretation of what antimatter is, and they realized actually you can describe antimatter in a different way. It's like a particle, exactly the same properties, but if you look at it traveling backwards in time. And in fact, in particle physics, we describe the interactions we see in things called Fineman diagrams. This thing on the right-hand side is a Fineman diagram. And you'll see here an electron coming in, an anti-electron coming in, and then they turn into light, and then they can turn into other things. But you'll notice the arrows on this. This is going this way, which is forward in time, but we describe this one going this way. That's basically an electron going backwards in time. So this association between antimatter and time travel, maybe Star Trek had a point. Maybe you really can do strange things with time. I don't know how to make a time machine. I wish I did, but it is interesting. Okay, the experiment that I work on is called ATLAS. It's the largest of the experiments at the Large Hadron Collider in Geneva, and that at the moment is the world's highest energy particle collider. The collider itself is located, as I say, at CERN. It's deep underground. It's about 100 meters underground on average. It's got 27-kilometer circumference. And basically, we put protons, the nuclei of hydrogen atoms, very simple particles, but and we send them in one direction, and we send another beam of them in the other direction, and then at various points we collide them and turn the energy of those beams into new particles. The actual accelerator is quite cool, literally. Each eighth of the accelerator is the largest superconducting system on the planet, and the temperature of the accelerator is below the temperature of free space. It's almost at absolute zero. It's actually colder than empty space. So I actually tell my astronomy friends that particle physics is obviously cooler than astronomy. Our experiment is huge. It's about 5 stories high. For illustration, there's 2 people. There's another 2 people up here that are definitely violating any safety regulations. And the whole thing sits underground. The point is, when we record all of our collisions, this is a graphic with another very dangerously placed person there, half of the tracks that we see, half of the particles that we produce, are actually antiparticles. Slightly less than half, because you start off with 2 particles, so you end up with basically one extra particle at the end. But essentially, all of the processes that we're doing here are generating, to a very high degree of precision, equal amounts of matter and antimatter. And that's the puzzle. I'll come back to that in a minute. People do sometimes ask, though, if you were going to make an antimatter bomb, how do you do it? So this is Angels and Demons, a terrible book made into a terrible film. They were talking about having 1 gram of antimatter to make this bomb. That would make a very good bomb. It would be about 3 times the power of Hiroshima if you annihilated that amount of antimatter. It's about 40 kilotons of TNT. Or I live quite close to a nuclear power station called Hisham. It's basically the output of that nuclear power station for 50 hours, all in one instant. But you could make a bomb if you could get, actually they had 0.5 gram. You could put it in a suitable container, accumulate it, transport it safely to where you wanted to detonate it, and then annihilate it. You could make quite an effective bomb. The only problem is, in ATLAS, sorry, I'll just go back one. All of the antimatter we produce in ATLAS annihilates almost instantly. So you have to somehow find a way of capturing it and storing it. How much antimatter, how much would the energy released from Atlas's experiments do? Well, if you wanted to warm up a cup of coffee, this is a question Tom Hanks asked actually, how long would it take us to warm up that cup of coffee? If we took all of the antimatter we produce in the experiment, and we put all of the energy from the annihilations into a cup of coffee, it would raise the temperature of the cup of coffee by about 1 degree per hour. Now, the trouble is Newton's law of cooling tells you that it will cool down by about 10 degrees in that hour, so you wouldn't even be able to keep your coffee warm with it. How long would it take you to get half a gram? Well, at the rate we do it, it would take how many? About 10 million years to accumulate the amount of antimatter that you need. And you also then need to store it. And the only way you can store it is by a very clever thing called a magnetic bottle, because you've got to keep this antimatter away from all of the other matter. And if it meets matter, it will just annihilate. So you can make charged antimatter and keep it away from other things using magnets. So we do have these things called penning traps, which can store antimatter. There's an experiment called Athena that's dedicated to looking at the properties of antimatter. If you did that, we could accumulate enough antimatter to make your bomb in about 500 million years, but we just can't make a trap that would store that amount. So, I mean, at the moment, we can store about 1/100 billionth of a gram, and that really isn't going to do very much. So it's not very realistic. However, antimatter is being produced and is useful. So I told you there'd be a really practical application. One of the really practical applications is, anybody had any themselves, or you don't have to say yourself, but anybody ever interacted with something called a PET scanner, a PET scanner? No? It's used particularly in diagnosis of cancer. It's called positron emission tomography. And basically, we inject something which will produce a small amount of antimatter into people's bodies. That annihilates. It's tiny amounts of energy. People shouldn't be scared about it at all. But it allows us to see very precisely from the energy of the photons coming out, we can very precisely see where it annihilated. And if you can get that to target onto, say, a tumor, you can make very precise imaging. It's tomography. It's imaging of things. So these PET scanners actually image things going on in your body using anti-electrons, the annihilation of anti-electrons. It's a very practical thing. By the way, there is also antimatter in the room today. I mentioned the uncertainty principle before, and I told you about if you know something too precisely in time, there's an uncertainty in energy. That means that actually, even in empty space, you are producing pairs of particles and antiparticles all the time. And if you work out the maths, and this is sometimes something that surprises even my particle physics friends, if you work it out, at any given time, you are about 15% antimatter. But that antimatter lasts for such a short amount of time that it annihilates again and disappears. And because of the laws of physics, the energy doesn't get liberated. It only borrowed that energy for an instant and has to give it back. So actually, we don't really see too much of an effect of that. But there is actually antimatter in you at any given instant. You can see evidence for that, by the way. If you have a vacuum vessel and you take 2 plates of metal, you find that there is actually a force between those 2 plates of metal that attracts them together. It's called the Casimir effect, and it's been established since the 1950s even. Why is that happening? It's because of those particle-antiparticle pairs being produced between the 2 plates. They do something called polarization. They make it almost like a little capacitor, and there is a force, actually, effective force, because of those particles that helps those plates pull together. Unfortunately, nobody's found a practical way of using that, but Fineman spent an awful lot of his later life trying to think of a practical way of using that. Okay, so back to the big question. What's the matter with antimatter? Well, the universe produced huge amounts of antimatter in the Big Bang. And by all the laws we have, to a very good approximation, it produced equal amounts of matter and antimatter. We do know of one process that tells the difference, distinguishes between matter and antimatter slightly. It's in the weak interaction, which is one of the nuclear forces. But it's a tiny amount. So if you produce equal amounts of matter and antimatter, what's going to happen? They're going to annihilate. But somehow we ended up with a universe where you and I are made of matter, and there isn't much antimatter around. I mean, people never knew about it until 1930. There's tiny amounts that are around. It's hidden. So where did it all go? Or indeed, what was it that generated a little bias towards matter over antimatter? Well, if you expect me to tell you the answer, I'd be out of a job, because that's what I'm trying to research. We don't quite know. We are incredibly lucky, by the way. You might think that this truck driving off the road here, which actually came off the road off the side there, it was quite lucky it didn't fall off the cliff. But actually, we're really lucky. This guy was lucky. He was much luckier than you think, because that's where he came off the cliff. That's trivially lucky compared to the way the universe has delivered us a universe made out of matter and not matter and antimatter together. Because, do the numbers, you find that to generate our world, you would generate 10 billion and 1 particles of matter and 10 billion particles of antimatter. The great annihilation happens, and then we get left from that residue. That is really finely tuned. It's a good job we're here. So where is this thing this is where it gets a little technical, don't worry, you don't need to understand the diagram. But essentially, we do know of one thing which does distinguish between matter and antimatter. It's called the weak interaction. And one of the places where we can see evidence for that difference is looking at decays of particles that contain one of the heaviest quarks called the beauty quark. So we call them beauty particles. And in their decays, and in particular I look at a decay where it goes to a thing called a J psi and another particle called a phi, you can see evidence for the fact that matter is being slightly favored over antimatter. It's an effect called CP violation. But the problem is, it's nothing like enough. Now, recently, another experiment at the Large Hadron Collider called LHCb has shown that there is a similar bias, which you can see between matter and antimatter, in particles that contain another sort of quark, the charm quark, which is a bit lighter. And that's really important that we establish that, but it's not enough. So where is this? Well, we're looking to see more effects from new physics which might be giving more of a bias. I can see I've got 4 minutes. Yeah. There is another set of experiments, for instance, neutrino experiments, look at how one sort of neutrino magically transforms itself into another sort of neutrino. There's an experiment, for instance, called T2K in Japan, which some of my colleagues in Lancaster work on, where they send a beam of neutrinos across almost 300 kilometers across Japan, and they see how one sort of neutrino turns into another. There is evidence from those oscillations, those transformations, that there is also a bit of a bias towards matter over antimatter in those sorts of particles as well. But the problem is, you add all of this stuff up together, it's about 1/10,000,000th of the amount of bias towards towards matter over antimatter that you need to explain how we end up in this room today being able to give this talk. So it's a really great mystery, and it's a great thing to go and research, because we like to try and understand these things. Okay. I have to wrap up now. I just briefly say that the ATLAS experiment is looking for more than just matter and antimatter. One of the other things it's looking at is a thing called dark matter. We're looking for dark matter. We find that there's not enough material, ordinary matter, in the galaxy, for instance, to explain the behavior of how it rotates. There is some other form of matter in there called dark matter, which is holding it together. Now, in fact, we only have about 5% of the universe we can explain with ordinary matter, and we need about 26% of it in matter form, so about a missing 22% is this dark matter. We don't actually know what it is. You can also see it in galactic cluster behavior as well. This dark matter is there. We don't know. We think there are theories that would produce new particles which would have been produced in the Big Bang, which would still be lying around and not decaying, which could explain it. But if that's true, we should be able to make them in experiments like ATLAS. And that's what one of the things we're trying to do, directly make dark matter particles. There are other things. There are theories of hidden dimensions, which explain a lot of the mysteries of physics. We're looking for evidence of those. That might explain why gravity is such a much weaker force than electricity and magnetism, electromagnetism. But we haven't got direct evidence for that yet, but we are looking for it. And of course, we're just looking for completely new stuff. We can't always be guided by theorists, experimentalists like me. We do experiments because we want to see what nature has, not what some guy thinks that nature should have. So, you know, we work with them, but they don't dictate everything. So we can bring our physics into a new territory because we're in a new energy regime. We're going to have huge data. We do have huge data sets. We have 600 petabytes of data that we analyze. That's one of the things that keeps me busy, is trying to get the whole computing system that can handle 600 petabytes of data working. And there could be new processes that will produce all sorts of new knowledge and may explain why there is this bias towards matter. We will learn more about the basic forces that shaped the early universe. What is the matter with antimatter? Well, I've told you what the problem is. What I can't tell you at the moment is the solution. As I say, right now we know the problem, we don't know the solution. We've had great discoveries in Atlas already. You may have heard about the discovery of the Higgs boson. That was a truly important discovery in the history of physics. Unfortunately, I haven't had any time to tell you about it, but maybe another time. Many questions remain for us to answer. And what I would say, if you are young and if you are interested in this and you're prepared to do a bit of study, why not come and join us? Because it's actually a great lifestyle, a great job to try and find out how the universe works. And I would encourage you, if you're interested, to follow that ambition, that excitement. All right, that's it for now. Thank you.